Having said that, we are now right on time to invite our first keynote of the day, Rupak Biswas, who I have been pestering to come to New Zealand for a number of years. And I succeeded. So, welcome, Rupak.
And again, thanks to Nicholas. Again, Nicholas has been hounding me. Maybe I'm not sure is the right word, but it's always been my desire to come here. But I'm glad I'm here. I spent about a week in North Island. Had some bunch of meetings with New Zealand Space Agency folks. And then here I am, another, almost a week in the South Island. It's an unfortunate year with everything that is going on with the US government and all of that. And there were some concerns that I may not be able to come at the last minute. There was also issues with various content in the slides. And so we'll see how much we can present. I haven't given the slides yet to Nicholas, but we'll figure something out by the end of this conference, I guess, or leaving New Zealand. I also apologize to some people who may have seen some parts of these presentations in different talks that I've given, but it's also, because of approvals and other kinds of things. So with that, let me start off first with, because I think there was a comment in Nicholas's numerous email messages that he sent out that there should be some connection to New Zealand. And so, well, there have been multiple connections with New Zealand between NASA and us. Perhaps the most interesting one is this collaboration with Rocket Lab. And so basically, this is the first private mission that they are planning to fly to Venus, because around 2019 or 2020, research found that there was a presence of phosphine in that atmosphere of Venus. And so the idea is that could we fly a probe, and we are going to use this Rocket Lab Explorer cruise stage that will send a small probe into Venus. And then the probe has only one instrument, which is this autofluorescing nephelometer, which is going to search for organics. Again, we are searching for life. One of the most interesting things that NASA does, the two main goals of NASA is, one, is does life exist elsewhere in the universe? And if you are a betting person, you would bet that absolutely life should exist somewhere in the universe. It is hard to believe that all the places in the universe, there's this little tiny blue dot is where life exists. So that's a big question. And then the second question is, can we extend life beyond Earth, human life? And again, when we're talking about life, is life as we know it. There are other fundamental questions also, how did life begin and all of that. But this is one of those missions. This has been delayed several times, but this is a collaboration with MIT, Rocket Lab, of course. And the idea is that this launch is supposed to happen from New Zealand. Not sure exactly where it's going to actually launch from, but it's supposed to be in August of 2026. And basically, there's going to be this probe. And if you look at that little profile at the bottom right, it's going to have about 270 seconds to shine this laser into the atmosphere, get the reflections from that scattering that'll happen, and it'll have to send all that data back to Earth before it crashes into Venus. So you have 270 seconds, and this all has to happen during that time. So what we have built, so the main contribution for NASA is the thermal protection system for both the aeroshell, both the forebody and the back shell, and there is a little window over there from which this laser is going to shine into the atmosphere, and then we have all the communication that goes with it. So again, this is a big, interesting mission for various reasons. One, of course, is going to Venus. It's a private mission. It's a collaboration with Rocket Lab. In fact, we just built all the aeroshell, and we delivered it. We built it at NASA Ames, and we delivered it to Rocket Lab's Long Beach facility for final assembly. And then, in fact, I'm going to meet with Peter Beck later next month, and then we'll see when this happens. But this is really a cool mission that we are looking forward to. Okay, so with that, so that kind of is a connection. There are other connections, of course. We hosted the Prime Minister of New Zealand last year. I was talking with Nicholas about it. He had invited me to come to New Zealand in September, but because of supercomputing and all of that, that didn't quite work out. But there's still an interesting picture, and I'm sure if there's anyone in the audience from Australia, probably will not like that. But we have a big hyperwall display, and when we were taking the picture, in front of the hyperwall, the Prime Minister was wondering where he should stand. And he said the best place to stand is so that he blocks out Australia, so that when his picture comes out, you can see New Zealand and the Prime Minister. So that's where he stood. And there are photos of that. If you want to care, I'll show it to you. Okay. So again, for those of you who may not know much about NASA or just has an impression about NASA being Apollo and the International Space Station, this is basically what all NASA does. Again, some of these priorities might change with the new administration, but one of the most important things is aeronautics, and the big piece of aeronautics is a sustainable flight. You know, if you think about how you just heard from Dan, and we all know how chips have become so much faster, but flying hasn't actually improved that much. It still takes a long time to fly from point A to point B. And we are talking about supercomputers, and we are talking about all these things. It just doesn't make sense. So we have to improve that. We have to be able to fly sustainably. And we must be able to fly supersonic over land. So all of the, and then there are the human aspects of it as well. There has to be single pilot operations. For example, one of the things that happens in cars versus airplanes is cars, you drive cars most of the time, except for the new self-driving cars. You drive cars most of the time, and then the car intelligence takes over when there is an impending problem. But for airplanes, planes basically fly by themselves, and the pilots are there to take over. But then there's the questions of training. There's a question of whether you can do single pilot operations. And then, of course, if you throw in all the drones and UAVs, how do you manage the space? Space operations, the main there, of course, is low Earth orbit. And we have been doing that. In fact, when you talk to people who are less than 20, 25 years old, it's interesting to think that there's always been someone who has lived off Earth for the entire life of those younger people. But it's still a fairly innocuous environment. You know, we have 7 or 8 astronauts on board. We have 500 people at JSC who's taking care of them. This is trivial in some sense. The question is, can you go to deep space? And how do you go to deep space? Can you go there sustainably? Are we going to have a model like we did for the moon during the Apollo mission, where we send some people up, and then we have someone flying a command module around the moon while astronauts go onto the surface of the moon, come back? This is not a sustainable way of doing things. So we have to build something like the International Space Station around Mars eventually, which we are calling Gateway, where we would have rockets take you to the Gateway, and then you go from there to the surface of the planet, whether it be Mars or some other place, and then you come back. But the problem then is, that Gateway is going to be like your vacation home. It's not permanently occupied. It's not like the International Space Station. And so things like autonomy and human systems integration, those technologies become very important because you're not going to be permanently or continuously occupied. Science, again, is a big piece of what NASA does because of a space agency, and then all the technologies that get developed because of space exploration. How does it affect life on Earth? How does it, percolate down to what we do? So this is, if you think about it, this is all the various aspects of the NASA that we are focused on. So the talk is slightly different from what Dan talked about. This is more about how does HPC, and in my opinion, HPC includes AI in my opinion. So I'm not actually, and if you think about And many of you have been probably attending supercomputing conferences for a long time. And when supercomputing started, it was all about supercomputing. And a few years later, they started added those bylines. It's about visualization and storage and networking, because those all became part of computing. And now maybe AI is part of computing, at least in my opinion. That's how I look at things. So again, I'm not going to spend much time on it, but we are a very distributed agency. We are all over the United States. We are a purely federal facility. So we are all civil servants, which therefore we get affected a lot by what is happening, unlike many of the labs or many of the other NSF centers, which are mainly contracted out. Other than JPL, the Jet Propulsion Lab, which is an FFRDC, all of the other centers are purely civil servant organizations. So fortunately or unfortunately, we work for the executive branch of the federal government. Good. So the organization that I actually run at Ames is a large organization of about almost 900 employees, and these are the main things that we focus on. Now, this is the part of my directorate, and obviously the focus here might be more on advanced supercomputing or supercomputing and AI, but we believe that these are all things that NASA needs for exploration. So the directorate that I run is called Exploration Technology Directorate, and the goal is that for an agency like NASA, what we ultimately care about more is our missions, detecting life elsewhere, sending humans to Mars, finding planets or in the universe, flying supersonic over land. And all of these technologies are what we need in order to do that. So in some sense, this is just enabling technologies. And obviously supercomputing is part of it, but intelligent systems, these are purely autonomous systems, could be augmented reality, virtual reality, could be software validation and verification. But a big piece also is human systems integration. Unless we are a purely autonomous civilization or a society. So we are just going to be sitting at home on our sofas watching TV, and autonomy will take care of everything. If you're not going to do that, a big problem is how are humans going to interact with machines? And in fact, the biggest problem that we now have with self-driving cars, with Tesla and all these other companies, is not the self-driving car actually. There's actually not a big problem with the self-driving car, even though you hear about crashes and other problems. It's the mixture of humans and self-driving cars on the road. Because of all things, and again, we may or may not agree on this in general, but we are supposed to be somewhat controversial. The biggest problem is actually the humans. They are the most unpredictable of everything. Yeah, there are software bugs, and I'm sure no software has ever been written that is bug-free. The problem is humans are inherently unpredictable. In fact, and many of you know this, I've been in the Bay Area for a long time, and when they were first putting out the self-driving cars, we could see people in Mountain View cutting in front of a self-driving car and jamming on the brakes just to see what happens. No one would do that in their real mind, because there would be a fist fight on the road if you did that, or at least some special words would be exchanged. But this is how humans behave, and so that is the problem. So the problem is, if we can go to a purely autonomous thing, life would be fine. It's this transition that is going to be the problem. And then, of course, the entry systems technology is something that we consider part of it, because supercomputing modeling and simulation and materials is a big part of it, because unless we are going on one-way trips out of Earth, we have to bring things back. Whether we bring humans back, well, we may want to send some humans one way, but other than that, if you want to bring them back, well, then we need that. And then even if it's not about humans, if you just want to bring samples back from places, well, you need the entry systems technology. So with that, I'm going to just kind of show you a little bit of all the various things that we do. When we talk about computing, again, at least within NASA, it's an enabling technology. We are talking about supercomputing, obviously, in general, but also all of the new technologies, whether it be neuromorphic as well as quantum. And I know there's some quantum talks that will be happening here. I don't know if we have talks on neuromorphic, but that's another thing that we are very much interested in. Um, and again, they're not all in the same class of things because cloud computing can be considered a business model as opposed to computing per se. And accelerator technologies could be considered disruptive as well. But also, the other two big pieces of this is we are talking about a lot of computing, which is basically you're putting it a small, talking about modeling and simulation, let's say, and Omar will probably talk about this. Uh, your input data set is small and you're just generating massive Q files and you're generating all these visualization things. But the other piece also of that is data intensive computing. So NASA has a lot of observational data sets, which are petabytes of data that we are bringing in that we then have to process in order to get some information out of it. And you might be using AI or machine learning technology on it, or you may just have to process that in order to make some decisions. So and the other, so that piece of our portfolio is actually open to everyone. So you could be sitting anywhere in the world, and if you want any observational data sets that NASA has, we'll be happy to send it to you, as long as you have a fat pipe and a big storage tank on the other side. So that also is considered part of HPC or AI, any way you look at it. The other thing that also makes things a little bit challenging for us in terms of these big supercomputers that we try to run, nowhere close to what many of you have. NASA's systems are fairly modest in that sense, but our workload is very diversified. So if you remember that previous slide where I was talking about what NASA does, if you're talking about building rockets and spaceships and other kinds of things, those are engineering things. So they're probably running on 2,000 cores, 4,000 cores, but I need to run many, many of those in order to make a decision. On the other hand, if I'm doing global ocean modeling, or I'm trying to develop efficient helicopters, and I want to look at a vortex core and revolve it 20 revolutions and see how it interacts with the fuselage and the trailing blade, then we are talking about large scale single. I want to just run a large case as big as I can. And then, of course, we also have, like I said again, because it's considered enabling technology, how is HPC going to be able to support what we do? This was a big deal during the shuttle era, because if I have someone in space and I want to make sure that and we had all those accidents even with all of that, I think that will become another piece of our portfolio in terms of providing readiness in order to make sure that missions that are already out there, and now with all the Falcon and the Crew X, and then of course whatever Amazon and Blue Origin wants to do. So those are all about maintaining readiness and being able to provide quick responses. So I thought I'll just show a few things that we are mainly working on, where a lot of this is on supercomputing capability, a lot of it is algorithms, but a big piece of what we do is not necessarily about performance. It's about accuracy. So by and large, even though we have several missions, we have a very focused things that we are looking at. So we like to run codes that we know are probably accurate because we have run them for a long time. And so if someone comes along and gives us an implementation of a certain code that runs 20% faster, maybe we are not that interested. If it runs 5x faster, perhaps, but then we are looking at the accuracy of the code. If I'm going to miss a star by, a few hundred kilometers, it probably doesn't matter that I got there faster. I just missed it still. And so one of the big pieces, and again, I start with aeronautics because, if you look at NASA, the first day is actually aeronautics. And that's how it all started. So a lot of work at looking at different concept vehicles that we might be using for air mobility, because ultimate goal is not to take an Uber from the airport to the hotel, but the ultimate goal is to go from point A to point B, and wherever A and B might be. And I, as a human, don't want to care about that. I'm at A and I want to get to B, and the system has to figure that out for me. That might include Uber, that might include air taxis, that might include supersonic flight over land, but I just want to go from A to B quickly. The other piece of all of this that also comes is not just about the performance and the stability of the vehicle, but how would the vehicle interact with a with a surface, for example, because humans will have to get in and out of these things. So there is also a question about the stability and the safety of a rotorcraft landing, on your rooftop or in the parking lot, and how would humans board and disembark from these vehicles is another big piece of what we are looking at with a lot of modeling and simulation. The most annoying things of airplanes is landing gear noise, and that is why property values in the approach areas to airports are very low, because by and large, this is the biggest source of noise and of annoyance to humans is the landing gear noise. And so we had done a lot of work with Gulfstream, but also with other airline companies, and we have tried to see what architectural changes could be made in that area of the landing gear. So, for example, if you put a flat plane below it, and again, there are experts here who know about some of these things in order to reduce this noise from the landing gear. I wanted to talk a little bit about going to Moon and Mars. Again, some of this, just to be absolutely honest, not sure how all of this is going to pan out in the new administration. But the idea was that we have this Artemis mission, which is a way to not only go to the moon, but stay there sustainably, rather than just going there for a couple of nights and just, plant a flag or something. Can we stay there for a long time? And then can we go from moon to Mars and places beyond? So we've already done Artemis 1, which was a test flight. Artemis 2 is supposed to be a crewed flight without any landing. Artemis 3 is actually supposed to land, and then we have other things beyond that. And the idea is that unlike aeronautics, which is still considered a competition between countries. So, if you're working with Boeing versus you're working with Airbus, you're probably competing with one another. At least for us, for space, we consider it, until some time comes in the future where there might be competition. For space, it's more of a human endeavor. So a lot of it is government and commercial partnerships. It's also partnerships with other countries. And because if you think about it, the Apollo model was a bad business model. That could never work, because the US government is going to make things and we are going to consume it ourselves. It's like you open a bakery and you are the sole consumer of all that. This is not going to work. And so we believe that that's not how it's going to work for the future, if you really wanted to get into space. So obviously, this is the biggest rocket that we're building. Again, we don't know what the future of this is, but this is the Space Launch System. This is significantly bigger than the Saturn V rockets that you've seen if you have ever visited Kennedy. And this is our rocket that is supposed to take humans to space. We do a lot of simulation, because remember, all these launch pads that are at Kennedy were built for Apollo. A lot of those had to be reconfigured because of different rockets that we have launched over the years. A lot of them have also been reconfigured because of what SpaceX wants to do or what Blue Origin wants to do. But this takes up a lot of our computing capability to see what is the geometry of the launch platform, what kind of ignition overpressure that happens before the rocket actually takes off, because it takes about a couple of seconds for the rocket to clear the tower. And during that time, there's going to be this ignition overpressure that's going to happen because of all the fuel and all of that. There's also a lot of acoustics. There's the stability of the rocket itself. And so here what we are trying to do is looking at the worst case scenario. So there is no water onto the launch platform. So we are looking at the worst case scenario of the launch. You can see some couple of green men here and there. They're obviously not standing there. They're just to provide some sort of perspective of the scale of things. And there is no end to the kind of simulation you want to do. You could do very simple things, or you can start also modeling individual rivets and make sure that you understand what the flow is around those rivets. This happens after you have launched, and you're now trying to separate the solid rocket boosters. One of the big questions here is the clean separation of the solid rocket boosters from the core stage, because you do not want recontact. And Um, the number at the bottom left shows you the separation of the distance between the tip of the solid rocket boosters and the main cruise stage, and 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 this again, this is not only algorithms but visualization as well as supercomputing capability to be able to do these kinds of things. Um, again, I wanted to give you a flavor of all the various things. A lot of the simulations are used also for ocean modeling and weather prediction. A lot of it is a combination of not just oceans, but also polar ice caps, the sea, the wind, as well as observational data sets that are used to kind of start these simulations. A lot of these things are done uh, through what we call data assimilation. So we have observational data sets from 50 years ago. And so we feed these models. And again, many of these are ensemble models also. We're not just running one code per se. Some code might be good at precipitation, another could be good at trajectories and stuff like that. So you seed these models with data that you have from 50 years ago or 40 years ago, run it to the present, and then you compare current observations with what this model is telling you. And once you feel that there is enough confidence, then you can use these models to predict the future, because now you've kind of vetted them in some sense. Many of you probably already heard about this asteroid, YR24. It's in the news. This was discovered, I think, December, around Christmas last year. I think this is between 40 and 90 meters, this asteroid is, as I think something like 90 megatons. It's supposed to hit Earth on December 22nd, 2032. So we still have 7 years time. Things like that happen all the time. I'm not trying to scare anyone off, and you can probably look up in Wikipedia. The first thing when I say this, people ask us, where is it hitting? Well, we don't know. This is still far away. And there are lots of things that we will do in order to prevent it from hitting Earth. But right now, that strip, the probability strip, I think, is just south of the equator, or maybe it runs over northern South America, through parts of Africa, through India. And so that's the kind of the path it's supposed to hit. The reason that we are concerned about it is because these things happen all the time. But if it were to happen, this would be the biggest event since the 1908, the meteor that we had in Siberia. The other problem is that the probability is increasing. It was 1.3% at the beginning of this month. As of yesterday, it's at 2.2% of hitting Earth. But again, we are 7 years away. So this is a simulation that we have been doing also for a lot of this. This is obviously a much bigger asteroid. This is 10 gigatons of energy hitting Earth. What would be the impact of that? Depending on if it lands on the ocean, what kind of tsunami you might have, and all the blast waves around it. The picture on the left shows that these things happen all the time. It's not something a rare occasion. It's these big things that come in that might be more concerning. The other thing that I talked about also is, as many of you know, it's about this thing called TESS. This came out of this mission called Kepler, which is trying to find other planets in the solar system. So, because remember, one of our main goals is to find life elsewhere in the universe. Okay. Now, again, life as we know it. And so if life as we know it is what we're looking for, then this thing, planets, let's call them, have to be in this Goldilocks zone. They have to be just the right distance away from the star. And then we're always debated about whether there are 8 planets or 9 planets, or whether Pluto is a planet or not. Doesn't matter anymore now, because there are thousands of these all over the universe. There are billions of these stars, and there are multi-billions of these things that are revolving around these stars. And many of them are, and that's one of the stars that we're looking at, and they are in that Goldilocks zone. So they are just the right distance away from the star. So they should be able to, and again, they should be able to harbor life. And again, this is where we apply a lot of our machine learning technologies, because what you're looking at is so for example, the test instrument is just looking into space and is looking at bright objects. And it sees if the bright object is dimming. And if the bright object dims at a certain periodicity, there must be something going in front of it. Okay? Now, again, there's a lot of luck involved, because if that thing goes right around the equator, that would be like the perfect dimming, but it could just barely be touching and you're going to miss it. Or the alignment of the star and your instrument and the planet are not aligned perfectly, so there is no dimming, so you don't know that. There could be other random effects that are happening. Some other things are flying in front of that star. So, but based on that, and again, a lot of this is community effort. So we are just getting these light curves. These light curves are available to anyone and everyone, and people have written papers on this, and you'll find or hear about graduate students somewhere who found a planet or something. And that is exactly what this goal is to find these potential planets somewhere in the universe that we can find life. So I'm going to end with a couple of things that are more futuristic, and then maybe we'll open up to questions. So one of the big things is Mars sample return. So this is a massive collaboration throughout the world, and the idea is that we want to bring samples back from Mars. Okay, but we have a couple of problems. One is we have to make sure that sample is not tainted. The second problem is we have to make sure that sample does not come and eliminate half of civilization, because we don't know what the sample has, right? So both of these are big concerns. And so we have already started that process. So we have had these rovers on Mars. They've already been collecting samples. The samples are getting stored. So if you look at that big kind of a pictorial thing on the right, so it's all done. Then we are going to launch something, which we don't know yet, maybe a helicopter, maybe a rover, which is actually going to collect all those samples from what Perseverance and others have put on Earth, on the surface. We're going to collect all of that, and then we'll have a Mars ascent vehicle, which is going to launch from the surface of Mars with those samples. And this is also a collaboration with ESA. We'll have another launch that is actually going to capture that orbiting sample. Then it has to be put inside a Earth entry system, make sure it's completely packed properly. And then the part we haven't decided yet, whether should we bring it back to Earth? Should we leave it in some orbit somewhere? Should we perhaps leave it on the moon? All that is still TBD. But this is not a single mission. This requires multiple launches from both NASA and the European Space Agency. There is the whole modeling and simulation aspect of it. There's the whole thermal protection system of a piece of it, but also the actual containment of the sample so that the sample stays inside. This is the other big mission. This is Dragonfly. And so this is a mission to Titan. And what we believe is Titan has exactly the conditions that Earth had about 13 billion years ago when we were formed. So the question is, if I can figure out what is going on in Titan, perhaps we know, unless you believe in creationism, we'll just leave that out for the time being, then we can probably figure out how life started on Earth. And so this is a mission that is a nuclear-powered octocopter. It's going to take 7 years to get to Titan. But once we go there, we are going to fly there because the atmosphere is heavy, so we can fly. And being able to fly a helicopter is so much nicer than driving a rover. It just takes forever. And if you think about the 7 minutes of terror, this is going to be many, many minutes of terror. And we have no idea once it is launched till it actually lands before we actually get a signal. But this is with Johns Hopkins APL. Penn State is doing a lot of work on the modeling and simulation as well. But this is going to be, several minutes of descent before we can actually get the helicopter out. and then we can fly all over Titan and see what the conditions there are. So I'm going to end with a couple of things. One is I talked about the observational data set. So we also have this thing called the NASA Earth Exchange, which is started off with Earth science data, but this is also a collaboration with Amazon, where we provide all of the data that we can collect through some portal, but we also encourage people to upload their modeling and simulation codes, their observations, because one of the biggest problems in the scientific community, and this is a big part of supercomputing as well, is reproducibility. People are having data, they're writing papers, they're doing something, but the next person has no idea how that happened or how do I take that forward. Again, I wanted to show you a little bit about all the other things about autonomy and human systems integration. So for example, on the International Space Station, we have these things called, we call them astrobees because they are like bumblebees or honeybees or whatever, and they're moving around and doing work that you don't want the crew to do. So maybe housekeeping, or maybe taking measurements of dew point and temperature. And they have all kinds of perching arms. They can go and charge themselves up. It's almost like a Roomba in 3D. But these things are going to become more and more important if we are in deep space. The other big piece is we talk about additive manufacturing or 3D printing. Well, those are all very interesting, but to be able to print a nut or a bolt or a little flat plane is nice, but I have to build a habitat. Just building me a brick in space is not going to work. I need to build a mansion on Mars from the bricks. So we have this project called Armadas, which actually builds the small building blocks, and then there are other robots that work together to build a larger structure, because we need large-scale structures in space, not small things. I'm going to skip on that. We do a lot of work on quantum computing, but again, I know there are other people that are going to talk about, but I wanted to just end with a few charts that shows, a couple of charts, again, it'll not take more than a couple of minutes, but it shows about, again, what are the things that we think advanced computing that this community is working on both hardware, but also algorithms and software that is going to take us to the next generation. Because one of the biggest problems in aeronautics is certification. FAA is not going to allow you to plane just because it does something that some computer science guy wrote some paper somewhere. This is not going to work. So the big piece of that is certification by analysis. So instead of flying an airplane, can I certify it through analysis? And again, this just gives you a notional thing. These are systems that we have had. These are systems that are in procurement, and we might get to some system, let's say, by the end of this decade. But this shows that, what kind of enabling supercomputing, HPC, or AI might be able to do for the things that we care about. So if you can do certification by analysis, that will be, if you go talk to Boeing or Airbus, it takes a long time from the time you actually build an airplane and we have passengers sitting on it. This is not a good way of doing things. The same with climate modeling. We are still doing, maybe a kilometer resolution, but now if you really want to do a meter resolution of the entire ocean, and now you cannot treat that as a homogeneous fluid. Now you have to look at kelp, and you have to maybe look at whales and dolphins, and all those kinds of things have to go in there in order to actually predict anything. But right now, if you're doing a 3-kilometer resolution thing, okay, you can ignore all of those things and say that this is an homogeneous fluid. Not correct. Everything that we do on Earth is dependent on the sun. And so if you don't understand the sun very well, about solar flares, about coronal mass ejections, that is going to impact what we do on Earth. And being able to predict these solar events that might happen is going to be an important part of communication. It's important for even the International Space Station. So I'm going to, and then of course the whole launch environment is another big component of what advanced computing might be able to do. So with that, I think I'm going to stop here, and I'll be happy to take any questions.
Thank you very much. And